Earlier, we introduced some basic concepts and defined data warehouse. The next topic, we're going to talk about the data cubes in a data warehouse and the OLAP operations it supports and why it could support OLAP operations. So a data warehouse, as we mentioned earlier, is based on a multidimensional data model, which views data in the forms of a data cube. A data warehouse consists of multiple data cubes. A data cube is focused on one subject. For example, a data cube for sales would allow data to be modeled and viewed in multiple dimensions. To support that, the schema used in data cubes are slightly different from the schema that we use to construct a relational database. In relational database, when we construct database schema, we analyze the dependencies among the data and use normalizations to decide what attributes or dimensions fields need to be included in which table, and how one table should be related to another table through foreign keys. In a data cube, because the need to support multidimensional data model, which is needed to support OLAP operations, the schema that we need to design for a data cube need to consider from the dimensions perspective. We will have dimension tables and fact table. Typically, you will have multiple dimensional tables, one table for each dimension. For example, for when you're talking about sales, you want to know which item was sold, so you have an item dimension. You want to know when that item was sold, so you have a time dimension. So those are the dimension tables describing the environment that sales happens. And the fact table contains the measures, such as dollars amount or items counts that's being sold. And because we need to associate the measures to the environment when the sales happens, we will have the primary keys from each of those dimension tables also included in the fact table. Okay, so this fundamental structure that's separating fact from the dimensions, this conceptual separation, allow us to design specific data schemas to model, to fit the data into a structure that's going to be useful to support multidimensional view, the drill up, the drill down and the roll up operations. Okay, and we're going to see multiple examples of that in the following slides. In data warehousing literature, n-dimensional data cube is called the base cuboids. The topmost zero-dimension data cuboid, which holds the highest level of summarization, is called the apex cuboids. The entire lattice of cuboids is a data cube. Yeah, this discussion is very abstract, so let's look at one example. So this is our sales data cube. The lattice, so the entire structure, this is a cube. A cube is a lattice of cuboids. So those are the cuboids. Remember we talked about multi-dimensional view. At the most detailed level, the data holds item, time, item, location, supplier. And then we can generate different combinations of selected dimensions to create aggregated data set at different levels. At the very top level, the most aggregated data, let's say the fact that we care in this cube is the count, how many items has been sold. Then this all cube holds only one value, total counts of the item that's being sold in the entire cube. Okay, and the bottom, the base cuboid, holds detailed information about each item, each specific item, and the time that it's being sold, the location that's sold, the supplier of the item. So that holds the most detailed information. From this cuboids, we can generate all the above. The reason we need to generate the all of the above is to support efficient query. So we don't actually have to do all those aggregations on the fly. We have something already computed that we can just access this certain cuboids to supply the answer to a query. Okay. So we talked about a cube, and now next we're going to talk about the schema. Earlier we mentioned the separation of dimension tables and fact tables. With that separation in mind, there are three popular data schema for modeling data in a data warehouse. So the star schema, the naming of those schemas are based on the illustration. This schema, if you visualize it, it's going to look like a star. So therefore, it's called a star schema. A star schema, you can read these descriptions, but I think it's more intuitive if we explain those schemas by looking at real examples. So this is a star schema for the sales cube. So remember we talked about fact and dimensions. And here we have time dimension, branch dimension, item dimension, and location dimension. And the facts that we care, those are the measurements, units sold, dollars sold, average sales. Okay, so it could be one or multiple measures that's in this table. As you can tell, every dimension has its own table. So this is a time table. And in the time table, we have fields, its primary key, day of the week, month, quarter, and year as the fields. In the branch table, we will have branch primary key and branch name, branch type. Okay. So for every dimension, we have a complete table, and the primary keys of those dimension tables are included in the fact table as the foreign key. So the complete sales fact table going to include the primary keys from every dimension tables. This allows each record in the sales table to be connected to the more detailed information in each of the dimension tables. And in addition to those the primary keys from the dimension tables, we have the real meat for analysis, which are our facts, the measures. So this example, as you can see, it looks like a star. right? You have this and all that. It looks like a star. Okay. Built on to the star schema, we also a second popular schema called snowflake schema. The primary difference of the snowflake schema to the star schema is the additional normalization that's done on the dimensional tables. So earlier, if we look at the city, the location table, we have city, we have state or province, and country. As you can imagine, if we have one city occurred many times in this cells cube, then we're actually repeating the state and country multiple times. As many times as this city name appears in the entire cube. So we can further normalize this. Use the same database schema normalization technique in the relational database. We can normalize this to create a separate table called city, and then create a new primary key to represent each city, include that city key in the location table, and then move all those details in the city table. This saves some storage room. So every time we only need to mention the primary key of a city. So for example, city ID. And then every city have a separate record in this city table. So we're not repeating the city information 20, 30, hundreds of times in the location table. That saves, similarly, we can actually normalize supplier. The drawback of this normalization is while a saved storage space, requires additional joint operations when we need to gather city, state, province information from the city table. We have to make this join and make this join to find those information. Join is the most expensive operation in database systems. So this is a trade-off. In majority of the cases, even the star schema is the simplest schema. It is also the most popular schema because it's conceptually simple, it's easier to maintain, and also efficient. The only drawback is the storage. As you know, that storage has become cheaper and cheaper. So this in practice, star schema is still the most popular. So we compared star schema with snowflake schema. As you can tell, when we have those additional normalizations might occurring on those dimension tables, the visual display of the schema is more and more like a snowflake. So this is why it's called snowflake schema. And then to further save space, as you can tell, when you have multiple factor tables, so this talk about sales, the other is shipping, we can tell that the factor tables actually share some of the dimension tables. So we can actually construct putting them in one place, in one data cube to cover both shipping and sales, because we can actually share those tables. It's more efficient, more effective in terms of the storage usage. However, it becomes more and more complex, right? This is called a galaxy schema, also called fact constellation. We have multiple facts table in the schema. It's used, but it's less popular than the star schema. So now we can go back and look at the descriptions of the star, snowflake, and the factor schema. I think when you read it, it will make much intuitive sense. Okay, so we talked about the three main data schemas used in modeling data cubes, and now we can look at in detail the location dimension that we have represented in the earlier examples, the location dimension. This location dimension, again, is a very good example to demonstrate the concept hierarchy the concept hierarchy concept that we have learned earlier. As you can see, the most detailed level is specific office, and then its city, its country, its region, Europe or North America, or all means this we actually so this is the entire globe, right? And dimension tables often have those kind of concept hierarchy. So, for example, branch name is very specific, but branch type is already at the upper level. It can potentially be used as a way to aggregate multiple branches that belongs to the same branch type. And time, as you can see, also has those concept hierarchy in it, from day to week, month, quarter, year, right? And items, you can have item key name, so those are very unique, but the brand name already grouped them, and then you can further group them by type or suppliers. So the dimension table holding those concept hierarchy, those again supports OLAP operations. Having talked about the concept hierarchies in dimension tables, we now need to talk about the facts, right? The data cube measures, the facts that we include in the fact table, have three main categories. Those measures are divided those three categories based on their computational efficiency. A lot of times when we have very large data cube and we want to compute those measures in a distributed way. So using parallel computation to divide a large data set, many rows to 10 millions or more rows into smaller chunks. So we pass through those smaller chunks into different computational threads and have them computed concurrently. And then coming back, we can get the aggregate value. This way will make the computation more efficient. For that reason, we need to understand that different computations are at different complexity level. The simplest is the distributive measures. Count, sum, minimum, maximum are distributive measures that can be easily computed using parallel processing. So the definition of distributive, the measure is distributive if the result derived by applying the function to an aggregate value is the same as that derived by applying the function on all the data without partitioning. Well, this is a very long and hard to read sentence, but let's use count as example, right? So to count every items in the entire data table, we can have a total count. If we distribute that into smaller chunks of data, and we count every of those smaller ones, a simple summation or addition of all those single counts will give us exactly the same number as we counting the items in this whole data set one by one, right? So this is distributive because counting on the large data set is exactly the same as dividing the counting of the entire data set into n partitions. And the partitions, the result returned from the partition, we only need the result returned from the partition, the individual counts returned from the partition to find the overall count. And you can do sum, min, and max in the similar way as count. So those are distributive measures. A second group of measures, for example, average, minimum, the minimum n, so the smallest n numbers, standard deviation, those are called algebraic measures because they can be distributed, can be computed distributively, but we need more than one thing returned in order to compute the total measure. Using average as one example, we can divide the large data set into smaller smaller partitions, and each partition we can find its average, right? But we cannot just average the average from each partition to find the total average. We actually need two parameters, the average and also the count from each partition in order to compute the total average for the entire data set. So here we must pass this m arguments that make no difference. N arguments the same as m arguments, which is greater than 1. If it's equal 1, then it's distributive. If you have to pass multiple parameters or arguments in order to compute the total, then this function, this measure is considered algebraic. It's a little bit more challenging than distributive. However, it can also be computed efficiently using parallel processing techniques. The holistic measures is the most challenging. And for holistic measures, a lot of times we estimate. We don't compute the exact value because you cannot compute them accurately using those distributive computing. Partitioning will not, you cannot find the median of the entire sequence of data by finding medians in the separate partitions. You have to literally go through the entire data set to find the median. So if there is no constant bound on the storage side need to describe this subaggregate, we considered those methods as holistic. As I said earlier, those measures try to avoid them in data mining because we need they are highly costly to compute on a large data set. Find ways to estimate those, or using, for example, instead of median, maybe we can just use average, use the mean. Okay, so we have discussed the dimension table and the measures, and we discussed the concept hierarchy in dimension tables and different types of measures in terms of their computational efficiency for the measures.